In this video, I'm going to show why lambda is a real number. Sorry, I can't find my marker. And why lambda is greater than or equal to 0. So let me first start off by showing why lambda can equal to 0. Or actually, I'm going to leave this as an exercise for you. If lambda is equal to 0, show that phi of x is identically equal to 0. If phi is identically equal to 0, u is identically equal to 0, and we don't care about it. Okay, so now I'm going to start. I'm going to assume right now that lambda is real and show that lambda is greater than 0. It's already not 0 by this exercise that you have in principle done or will do. Now I want to show that lambda is greater than 0. Okay, actually the computation I'll show will show that it's greater than or equal to 0, but we already know it's not 0, so that it has to be greater than 0. Okay, come on now. The tension in the cable is pulling this a little bit. Okay, so we're going to start. So this computation that I'm doing is a very standard type of computation. I'm using the fact that when I integrate two functions, it's an inner product. And even more, in addition to that fact, the functions are going to satisfy these boundary conditions here. Okay, so I'm going to do lambda times phi times phi. Okay, so that's phi squared. So it's going to be important that this integral is greater than 0. In principle, it's greater than or equal to 0, but the only way it's equal to 0 is if phi is identically equal to 0, which again, we don't care about that case. So now this is going to be the integral, and I should write from 0 to pi. This is going to be the integral from 0 to pi of lambda phi times phi. But now I'm going to use the fact that phi satisfies this equation here. And I have this constant drift that is going on. Sorry to fix this right in the middle of the video. But like I said before, Tom Scott says it's a good idea. At least that's what I'm interpreting one of the things he said. I know Tom Scott, though. Or maybe I'll take you to a reactor or something. All right. Okay, so this is lambda phi times phi. Okay, and now if phi satisfies this equation, lambda phi times phi is minus phi prime. I just moved the minus sign over there. Okay, so this ends up being minus the integral from 0 to pi, phi double prime, phi prime. So now I'm going to do integration by parts and move that derivative onto the other phi. And so this is going to be equal to minus, okay, so now what's going to happen here, using standard integration of parts notation, this is like v prime, this is u, so I'm going to get u times v, which is phi prime times phi evaluated from 0 to pi, minus the integral from 0 to pi of phi prime times phi prime. Okay, now here's where the boundary conditions are very important, because it implies that this term is equal to 0, because phi of pi is 0, and phi of 0 is 0. Okay, so now the minus sign there and the minus sign there are going to cancel with each other, and because I need the space, I'm just going to rewrite this. This is equal to 0 by the boundary values, and then minus times minus is positive. Okay, so what we're going to be left with now is the integral from 0 to pi of phi prime times phi prime. Okay, well, let's make an observation here. This is greater than 0. Actually, we only know it's greater than or equal to 0 because phi could be a constant. Okay, so you know this is greater than or equal to 0. We know this is greater than 0. I've got lambda times something that's greater than 0 is equal to something that's greater than or equal to 0. If this integral is equal to 0, it means lambda is equal to 0 because this integral is not equal to 0. If this integral is equal to 0, it means lambda is equal to 0. But we've already thrown out the case. We were already assuming that lambda is not equal to 0. So lambda is not 0, this is not 0, so this integral is not 0. Okay, so it means that this integral is positive. If this integral is positive, it means this is positive. if this is positive, lambda has to be positive because this integral is positive. So this is positive implies this whole thing here is positive, okay? But since we know this integral is positive, it means lambda has to be positive. Since if lambda was negative, a negative times a positive is negative. So therefore, this shows that lambda has to be positive. Okay, now I'm going to do something, and it's going to make sense in just a moment. That shows that lambda is positive. If lambda is real, that shows that lambda is positive. Okay, so now I want to show that lambda is a real number. And I'm going to show lambda is a real number. I'm going to have to erase this, but I'm going to show lambda is a real number by showing that lambda is equal to lambda bar. Because if I have a complex number and it's equal to its own conjugate, if a plus ib is equal to a minus ib, that happens if and only if b is equal to 0. But if I have a complex number and the imaginary part is 0, then it's a real number. So that's what I'm going to show. And I'm going to do something a little bit sneaky here. I'm going to look at this integral, and instead of integrating phi times phi, I'm going to integrate phi times phi bar. So I don't know at this point, so I'm sort of going back in time and saying I don't know that lambda is real. So I don't know if phi is going to be real or positive, so I'm allowing here the possibility that phi could be a complex number, or that phi of x could be a complex number. So phi times phi bar, that's the modulus of phi squared. Okay, so it's still a real number here. Now over here, again, how did I get from this step to this step? I just used I just put the lambda on the inside, so I'm going to put a bar there as well. Those two things are equal. Again, going from this step to this step, I just used the differential equation, so I'm going to have a bar there. Now going from this step to this step, really what I initially have would be something like this. A prime on the outside of the bar, but the prime and the complex conjugate, differentiation and complex conjugate, you can do that in any order. And just, if you want to know why, just think about the difference quotient. Like, compute the derivative of phi using the difference quotient. And so really I've got the phi prime on the inside here. I got those backwards. I want the bar to be in red. So in other words, to show that the prime and the complex conjugate commute, just compute this, the derivative, with from the limit definition with the bar on top, and you'll see what happens here. Okay, so now what I'm going to do is I'm going to do integration by parts again. I'm not going to write the details, but I'm going to do integration by parts again. Again, use the boundary values, so the boundary terms are going to be equal to 0. And I'm going to take the last derivative off of this phi and put it on that phi. And what I end up with is going to be the integral from 0 to pi phi double prime bar. Sorry, with the negative sign from the integration by parts. Okay, but what is phi double prime equal to? Phi double prime is equal to minus lambda phi. So this is equal to the integral from 0 to pi. I've got my minus sign there, phi minus lambda phi like this with the bar. The minus lambda phi is going to come out. Minus lambda, sorry, the minus lambda is going to come out of the integral. The complex conjugate of minus lambda is minus complex conjugate of lambda. So when it comes out, the minus signs are going to cancel with each other, and we're going to have lambda with a bar on it. Okay, so notice what's happened. I've got lambda times this integral is equal to lambda bar times that integral. I know this integral is not equal to 0. This integral is greater than 0. If it was equal to 0, phi would be the trivial function, and we don't care about that. So lambda times something greater than 0 is equal to lambda bar times something greater than 0. By the same thing. It's lambda times a quantity that's non-zero is equal to lambda bar times the same quantity. Therefore, lambda is equal to lambda bar. In other words, lambda is real. Okay, so so this computation that we did here, starting from there, going to there, doing integration by parts twice. I want to talk just a little bit more about this. We will we will talk more about this in upcoming weeks. But what I want to talk more about is the following. Let's say I have this differential operator, L phi is equal to minus phi double prime. Then I can think about the integral of phi times psi. I can think about this as an inner product. So I'm going to integrate phi times psi. And if you don't know we're dealing with real functions, you need to put the complex conjugate there. But if we're just dealing with real functions, which I'm just going to talk through because it's a little easier, and that's what we're dealing with here, we can just write it like this. Okay, so what I want you to show you, or what I want you to do, is compute something like lambda phi times psi. In other words, what I want you to do is I want you to compute the adjoint. When I say compute this, I meant compute the adjoint. So what the adjoint would be the operator that satisfies this. So in other words, start this, do a lot of integration by parts manipulation until you don't have any operator on phi, you just have phi, and then whatever is on psi is going to be the adjoint of L. Okay, I'm saying this very, very vaguely. And you're going to assume that phi and psi satisfy the boundary conditions. They satisfy the boundary conditions. Okay, that's one exercise I want you guys to think about. Another exercise that I want you to think about is the following: if phi lambda double prime is equal to minus lambda phi lambda, and phi gamma double prime is equal to minus gamma phi gamma, and phi lambda and phi gamma both satisfy these boundary conditions, then I want you to compute the integral from 0 to pi of phi lambda times phi gamma. Okay, and for all of this, for both of these problems, we can consider either real functions, in which case there's no complex conjugate, or we can consider the possibility of complex functions, in which case we should put a complex conjugate bar there. Okay, that's it for this video, showing that lambda is real and greater than 0. I hope you're convinced.